Alright, so in this video I'm gonna be explaining this important paper with the title Optimal Time Complexity Algorithms for Computing General Random Walk Graph Kernels on Sparse Graphs. This paper in 2024 by Google Research. So we present the first linear time complexity randomized algorithms for unbiased approximation of these general random walk kernels for sparse graphs. The previous fastest methods were cubic time, order of n3, but now we want a linear version of that. So this is a graph kernel, random walk kernel between two graphs. We create this adjacency, which is on the product of the two graphs, G1 and G2. Like in this picture, for example, G1 is this, G1 is 2, and G1 times G2 is this product graph with the corresponding adjacency matrix. So the first order of n algorithm for the unbiased approximation for labeled and unlabeled graphs is called graph voyagers. And finally, you will see at the last slide that they compared these graph voyagers with the exact computation of graph kernel to see that it has some improvements. So this is our graph random feature that you are familiar with in the previous videos. The same thing. So we define this graph random features. Omega is prefix subwalk of omega of v sub I. This length is the number of hops that the walk. Whenever you see this, it means the last index, the last vertex of walk omega. And E sub k is the unit vector for coordinate. But this distribution, this is sampling walk omega. This is a probability of, what is the probability of sampling walk omega? The naive approach to calculate the graph random features is order of n squared. It's quadratic. C and D are constructed from independent graph random features. So we have quadratic complexity. For every pair of inputs, you should calculate that, which is very expensive. Especially, even if the inputs are sparse, it has problems. And so we want to have a linear algorithm to calculate or approximate this random walk kernel between the two graphs. For unlabeled graph, we can write this like this. To incorporate extra factors of I, we propose to multiply the estimators of the i's powers by a shared random variable g with zero mean and unit variance. So we call these g variables. What about labels? Then for labels, they added this z variable. Then after that, we say, what about random variables and labels, and then putting it all together, we have this kernel random walk that is in equation 8 between the two graphs. So the time complexity of computing each of the curly brackets is order of n sub I, r sub I. So it's linear in the number of graph vertices. Now they talk about scaling with number of nodes, scaling with number of graphs. While the analysis above has focused on approximating the random walk kernel with just two graphs, the graph level random features from this equation can be constructed for every graph in a set. The g and z variables must be cached and reused to compute every graph's feature. The Lorentz decomposition of graph matrix is important because it unlocks better scalability with respect to the number of graphs, in addition to size n. So this is the algorithm for computing to estimating the random walk kernels. We have modulation function f here. We have termination probability p of halt. And we have the number of walks m, so we need to loop over the number of walks. And finally, it returns x sub I because it is needed to estimate random walk kernels. So the good property of these G Voyagers is that they are unbiased, and it is proven. Also, a very sharp estimate is via upper bounded by this very good sharp estimate when we compare with the expectation of your kernel. So there is a very sharp estimate. And they did it for these graph classification data sets. You see, when we calculate using G Voyager L, we have improvement in classification accuracy in comparison to the case that we are using the exact random walk kernel. So this graph kernel learning is beneficial in downstream tasks, providing extra motivation for developing such algorithms.